My name is Carliane Vale. I will present the paper, a co-training based algorithm using confidence values to select instances. This paper is included in the machine learning field, more specifically in classification tasks. In this area, there are three approaches: supervised, unsupervised, and semi-supervised learning. We work with semi-supervised learning. For each approaches, there are many classification algorithms. We are working with the co-training. We observed that the process of automatic assignment of labels was a difficult task. Specifically, the random choice of the unlabeled example to be labeled. In order to smooth out this problem, Rodrigues proposed a confidence parameter to guide the labeling process of the self-training methods. Our objective is to present a robust extension of the co-training algorithm, which uses a confidence threshold as a selection rule of the unlabeled instances. The main advantage is during the labeling process, this method selects only instances whose confidence in prediction are higher than or equal to the threshold, so that they are considered reliable. The semi-supervised learning mechanism proposed to treat datasets in which only part of the data is labeled in order to obtain a better classification. The co-training increases the labeled set of data by iteratively classifying the set of unlabeled data and moving the most truthful prediction instances to the labeled set of data. The co-training process starts creating two distinct views of the dataset. Then, it generates the supervised classifiers C1 and C2 using the labeled data of view 1 and 2 respectively. Then, it classifies the unlabeled dataset of view 1 and 2 using the C1 and C2 classifiers respectively. The next, it adds to labeled dataset of view 1 and 2 the instances selected in the previous step, predicted by the classifiers C2 and C1 respectively. If the unlabeled dataset is empty, finish the process. Otherwise, restart the process using the new labeled dataset. This is the co-training with fixed threshold, CT-FT. The main difference of original co-training and this method is in the dashed box. Then, the CT-FT starts creating two distinct views of the dataset. Then, it generates the supervised classifiers C1 and C2 using the labeled data of view 1 and 2 respectively. Next, it classifies the unlabeled dataset of view 1 and 2 using the classifiers C1 and C2 respectively, after which it selects for each view the instances with confidence higher than or equal to the threshold. Then, it adds to labeled dataset of view 1 and 2 the instances selected in the previous step, predicted by classifiers C2 and C1 respectively. If the unlabeled dataset is empty or there are no instances with minimal confidence, finish the process. Otherwise, restart the process using the new labeled dataset. For the experimental methodology, we used 30 classification datasets. Each dataset was split into two sets, a training set with 90% of the instances and a test set with 10% of the instances. All datasets were originally labeled, so it was possible to perform 5 different configurations using 5, 10, 15, 20 and 25% of the initial labeled data. We apply 4 different classifiers in the training test procedure: naive-based, decision tree, KNN, and role-based classification algorithm. The initial confidence threshold was 0.95. This table presents the average accuracy and standard deviation of all methods with naive-Bayes decision tree, Reaper, and KNN. The numbers in bold represent better performance than original code training, OCT. The CTFT obtained higher accuracy than the OCT in all analyzed cases. As expected, the accuracy of both methods increases as the percentage of initially labeled instances increases. When using 5%, the initial training sets are usually very small. Consequently, this classifier will not be able to classify efficiently the unlabeled instances. The difference in performance when increasing from 5% to 25%, the percentage of initially labeled instances was not that big. At the end, OCT and CTFT have high standard deviation values because the values presented in this table are averaged over 30 datasets. As these datasets represent different classification applications, the analyzed methods tend to have different performance over these 30 datasets, leading to a high standard deviation. This graph presents the percentage of instances labeled in each method separated by classifier. Looking at the blue bar, we observed that OCT labeled all the instances. Then, as CTFT uses a fixed threshold, it does not label instances whose confidence rate is lower than the threshold initially set. Consequently, the set of labeled data may only contain those instances whose prediction is reliable. It affects positively the prediction of the classifiers. As a consequence, it improves the effectiveness of the co-training testing process. These results show that including low-confidence instances in the labeled set may deteriorate the performance of a semi-supervised method. Then, a more meticulous selection rule can have a positive effect in the performance of these methods, and this is the main motivation behind the proposal of CTFT. This table presents the p-value with Wilcoxon test for each classifier for each percentage of initially labeled instances. It's possible to observe that in all cases the p-value was lower than 0.05. Then, the proposed method provides higher accuracy than the original code training statistically. We presented the code training with fixed threshold CTFT, which an extension of the code training including a confidence threshold as the selection criterion to include new instances in the labeled set. Both in terms statistics and average accuracy of OCT, each of the results obtained demonstrated that CTFT significantly improves the performance. Then, not labeling all the instances positively affects the performance of the classifier. Thanks.